Good afternoon, everyone, and welcome. This is a lecture that I'm recording for Math 3034, Introduction to Proofs. Hopefully you can see the board, my office board here. I'm going to give a presentation on general unions and intersections of sets. This is section 3.6 of the textbook, which I'll follow fairly closely. So let's start. We actually had talked about this for just a little bit. The last regular class meeting before spring break, we did some examples. Today we're going to focus on the formal proofs that involve these things, and for that, of course, we need definitions. Let me just remind you of the setup. Again, I'm sorry if I temporarily block things. I'll try to move back frequently so you can see it. We're going to have a whole bunch of sets, A sub I, that are indexed by little I, that come from some sort of index set. Capital I, say. So we have this capital I, and we also have all these other sets, A sub I, A sub little I, for each little I in the index set. Little I, recall, was a particular index. And this lets us talk about potentially infinite families of sets, not just like two sets or even finitely many. Maybe the capital I might be the set of positive integers, or even the set of real numbers, or there could be all sorts of sets. And what we want to do is we want to take the union and the intersection of the sets in this collection. And we did, again, some examples, but I didn't actually define officially what that meant. So let's do that. So first, the general union. And like our other definitions of set operations, we need to say, well, what are the members of the new set that we're defining? What does it mean to be a member of this union? So for any object Z, here's what it means. Z is a member of the union. So it's a gigantic union symbol here with the index I in I. You put that underneath. So there's the notation I'm about to define. Z is a member of the union of the AI as I ranges through the index set I. And essentially, that means that Z has to be a member of at least one of the individual sets A sub I. That's an existence statement, so that the definition text has the quantifier. There exists I in I. Z is a member of AI, and that's the definition for the union. And then we can do something similar for general intersection. And here the idea is that to be in the intersection, you have to be in all of the individual sets. So for all Z, by definition, Z is a member of the intersection of the A sub I's, I ranging through I, capital I. By definition, that means for every index, little I, in the index set I, Z is a member of A sub I. All right, and the thing about this, because these quantifiers show up in the definition text, this is just a very good concept for practicing proofs that use quantifiers. And a theme to keep in mind as we do these proofs, which we'll come to in a moment, is to just keep track. Let's see if the color works here. Keep track of how you use or treat a known quantified statement of either kind, for a known for all statement, or a known there exists statement, compared to how you treat such a statement that is to be proved. As we have seen repeatedly, this is one of the reasons the status words are so crucial. The way a known statement is treated in a proof of whatever kind is totally different from the way that very same statement is handled if it's the goal, the thing you're supposed to prove. And we'll review how all that works. Of course, we have the proof templates for proving an existent statement, prove a universal statement, but we also have some rules in hand for what do you do if you already know a universal statement or you already know an existent statement. How does that help you do something else? All right, so that's one thing. Another thing I just want to briefly mention is just compare this to what it looks like if we had something like, what if there were actually just 3 sets and they weren't indexed? We just had A, B, C, and we said, well, what's the union? What does it mean for Z to be in the union of A, B, and C, which we talked about before, of course, quite extensively. Well, what did that mean? It meant that Z was a member of A, or Z is a member of B, or Z is a member of C, inclusive or. In other words, Z had to belong to at least one of the 3 sets going in. That's exactly what's happening up here, except you don't, if there's infinitely many sets, you don't have room to write them all. So you write them in this sort of condensed way, but it's conveying the same meaning. Now, though, you need the quantifier. You're not really allowed to join an infinite number of things together using the or. All right, so that's one of the things that the quantifiers help you do. And similarly, for the intersection, if it was just 3 sets, you use and. Z is a member of A intersect B intersect C. By definition means that it's a member of A and B, and it's a member of B, and it's a member of C. In other words, it's a member of all of the input sets. There's just 3 of them, so you can use and there. But in the general indexed case, you would have to use the for all, as we did. But it really is the same thing we did before, generalization of it. But you see the quantifiers showing up instead of the ors and ands. Nevertheless, there will be very similar properties if you're used to the properties that we had before. These upcoming properties won't be too shocking, hopefully. Although it is weird, like when you've got the index set, you've got all sorts of stuff to worry about. So we're going to look at some proofs in a moment. All right, so one drawback of this is that there's only so much room on this board. Maybe there's still a little bit of room left. I apologize for that and many other inadequacies in these presentations, which has been necessitated by the unusual circumstances we are in. Anyway, so let's take a look at some theorems and proofs here that use these new definitions. I guess you can always go back in the video so I can erase stuff and you can still see it by backtracking. But anyway, so theorem on general unions and intersections is, well, it's in the book, right, that I've made available to you. It's also on this handout, C Set Theory Handout 2, which has been posted in the course website, Canvas Files, the same place everything is. And I hope this isn't too ridiculous, but just if I can, I don't know if this was visible at all on the screen. This is the handout I'm referring to. It's got not just the new stuff here, but kind of a lot of other stuff we talked about before the break about, there's a theorem on product sets at the bottom there. And on the back is this theorem I've just referenced. Again, obviously you're not going to copy this down. You have access to this handout. But these are the properties we're about to look at. We'll look at some of them. And then I made some remarks at the end. Sorry for my bad use of the camera. But anyway, the handout point is it has a lot of helpful information, not just this. And of course, all of this is also in the book in various locations, but the handout kind of brings it in all in one place. I won't write the theorem on the board with all the parts. That would take a long time. We'll just write the parts that we prove as we prove them. At some point, you're going to want to try to remember and memorize. I realize there's all sorts of theorems here. The theorem statements will all come back in later courses, so eventually you want to memorize that. But the crucial thing to memorize right now, of course, are the new definitions and all the definitions we had before. So that when you see this thing in a proof, or this, you know you can replace it with this definition text that has the same logical status. If it's already known, then this is known. If this was to be proved, then you would be proving this. And we'll see a lot of that in just a moment. I'm tempted to pause the video while I erase, but I don't want that to potentially ruin the whole thing, so I won't risk it. You can certainly fast forward through this, I suppose, or spend the time memorizing things while I'm erasing. I hope you're all doing okay, not freaked out too much by everything that's happening. All right, so let's start with some proofs here. Let's see. So the first one I'm going to prove is this part D, using the numbering on the handout. What was called the lower and upper bound. So in other words, I'll write when I'm proving it, I'll write it, of course. Prove for all k and I. The intersection of all of the a sub i's is contained in AK, which is one particular set among the ones whose intersection is being taken. And also, AK, one particular set among all of these sets that we've got, is going to be a subset of the union of all of the sets we're looking at. By the way, I didn't write the setup, which is the same setup from the beginning. We have an index set. We have all these sets AI and BI. So that's all understood. I also always assume the index set is non-empty for somewhat technical reasons. That's something we want to do. I'm not writing that on the board, but that is part of what we're doing, what we're assuming. Okay. And what I kind of like, although I don't really imagine everyone's going to do this, is when we're proving these things, or when I'm proving this on the video, what you should really do is sort of stop the video and, like, at each step, try to write the proof yourself, or think, what am I about to say? What am I about to write? And why? What definition am I about to use, or what proof template? Because that's the sort of thing you'll eventually have to do on homework and exams and later in your life, right? Anyway, so for instance, pausing here for just a moment and looking at this statement, this entire statement to be proved, and thinking about what kind of statement it is, you're thinking you should all be coming up with this sentence in your mind for the first sentence of the proof. A little pause here to let you think of that. And that first sentence is going to be fix. Fix an arbitrary index k in the index set. Why? Because this overall statement is a for all statement. Don't forget, just because it's written in words, there's still that's outside of everything. So we're proving a for all statement. We have to fix the generic constant, in this case k, in the given set, and try to see what's going to happen with the rest of the statement. Okay. So now the rest of the statement to be proved is an and. So that means a two-part proof, because that's how you prove and statements. So part one is to prove this. prove the intersection of all of the AIs is a subset of the particular set AK. It's one fixed set now because we fixed the index. Okay. Later we'll do, maybe I'll just, I'll write it later. Part 2 will be this. We'll get to that. I don't know how much board space I'll need. And in general, I won't maybe use this, well, I just have to fit everything on the board. So I'm not always going to use the best formatting in the world because of the limited space. That shouldn't prevent you from doing that when you write stuff up. All right, so now, again, you should think, all right, what am I about to say when I'm doing part 1? New goal, right? And this goal is a subset statement. And that should make you think of a template which will automatically create 3 more lines of the proof. For subsets, to prove a subset, we're going to fix an arbitrary object, call it Z maybe, or whatever other letter. Assume Z is a member of the left-hand set. Whatever it may be. In this case, it's a general intersection. And prove, as a new goal, that this Z is a member of the right-hand set, as an AK in this case. I'm underlining these status words that I'm still using, logical status words. All right. And then every time you do this, you get a new goal and you maybe some assumptions to work with. In this case, and this is where the new definition appears for the first time in this proof, Z is a member of the general intersection. And it's already erased, but you've already memorized it. What does that mean? We've assumed that for every I in the index set, Z is a member of AI. We're still proving this. And so this is the first place where this theme comes in. An assumed statement in a proof has the same status as something that's known, temporarily anyway. So now we know or have assumed a universal statement. Okay. So the next step is not to fix I and I, etc., because that would be what you're doing if you're proving a universal statement. No. Here we already assumed it, but how are we going to use it to do stuff? Okay. And for this, you might, as we talked about it a while ago, but this is where we get to use this thing called the inference rule for all. It's really the definition of all. It's another way to think about it. This is what I called it before. If you know a universal statement, you know that statement holds for any choice of this I that you like, as long as this little I comes from capital I. Okay. Well, it just so happens that at the beginning, we fixed some index k that is in capital I. That's part of what we did up here. That's why this line is crucial. Okay. So I can replace I, the general variable here, by a particular thing in there, and replace the I by k, noting carefully that that is in the index set by, I'll call it star. This thing is star. K does belong to capital I. And we see, then, that the inside statement becomes Z is in AK. Okay. Now, this is actually basically a very simple and straightforward deduction step, but it confuses people all the time. Every time we do this, everybody gets confused by this, at least at some point. So, partially because the letter seems to be changing, but that's fine. As long as you can replace it not just by another letter, but by some expression, some long thing, as long as it was in the universe, capital I. And as long as you already knew this universal to be true, which we do in this case. Okay, so focus on that, and this, make sure that seems okay, because that'll happen a lot, especially in this section. Anyway, so that's now we've done this. That's the end of that. We still have to do part 2. Part 2. Prove this guy. So that's another subset statement. So we're going to do the subset template again. And Although we could reuse the z, that's allowed. Part 2 is separate from part 1. For safety and avoiding confusion and so on, let's use a new letter. Let's fix, say, y, arbitrary object y. You could use other letters as well, of course. Assume y is in the left-hand set. Prove y is in the right-hand set, which is this union here. All right, so that's the subset template. And now the assumption can't really do anything with that, can't expand it anymore. But this is a defined concept in the goal. So let's keep going with that. Prove, and so this is another definition we just had that hopefully you memorized. And this is the one where you have to say there exists an I in I, such that y belongs to a sub I. Right. By definition, this is what our goal means. Okay. And now, so again, this idea of different types of quantifiers, are they assumptions, are they goals? Here we had an assumed universal. Here we have a to be proved existence statement. So we need that proof template, which, as you should remember, when you're proving an existence statement, you, the proof writer, have to choose an example of an I that works, whatever that means. It means that the thing you choose better belong to capital I, and it better satisfy that. And given what we've assumed, essentially the only thing you can possibly do is to choose that I, that the example you're trying to make, to be K. This particular K was still fixed. This is still in force over here. We still have this fixed index known to be an I, because that's what we did at the very beginning. So that got used. And note, now we have to prove this thing here with I replaced by K, but that's the thing we just assumed. So it does work. And that's the end of the proof. All right, so there's one proof. Let me draw a little picture here as well. So it's hard to draw these general union things and stuff when there's infinitely many sets, but you can still kind of think of some sort of Venn diagram where there's all these sets floating around. And in this particular proof, we had singled out one particular one called A sub k. Maybe that's this one. And let's just make sure we have some intuition for what was being said. This first part says that the intersection of all of these circles, which I probably won't be able to draw correctly and not miss something, but it's probably sort of the stuff right here, or maybe even smaller than that, has to be the points that are in all the circles at the same time. That little tiny set is a subset of this sort of orange circle, which in turn, the orange circle, that set, is a subset of the union, which is, if you were going to shade that in, you'd shade in sort of everything that's in any of the circles. And of course, that's going to be a much larger set than this one guy, but this one guy is a subset of that. So it's saying something reasonable, but again, you have to go through this proof. You can't actually draw the picture in the infinite case for general sets. So we need all the logic. Okay. All right, 23. I'm going to break the video up at some point. Hopefully there's room for one more proof. I don't want to make any one video too long and then discover later that it's like the recording didn't work or something. But let's do another one, and then I'll have a part 2 where we'll do even more. Oh, and one thing I meant to say earlier with this notation, just like the quantifier notation, you're allowed to change the index letter, the lowercase I, to any other unused letter. So, like, if you want, instead of saying I and I, you could have said the union of like M and I, of A sub M, or the union of t and I, a sub t, etc. The capital I stays the same. Whatever the index set is, you not only just change that without changing what the set is, but you can, what the name of the index is anything you want, basically. And this comes from the fact that this is basically, when you expand these definitions, you know, for z to be in here, you have this existence statement. You'll recall that we were allowed to change the letter of the quantifier in both places without altering anything. Again, assuming m or whatever didn't already mean something else in whatever proof we were doing. So keep that in mind. All right. I really hope this doesn't like run out of memory or something. We'll see. Okay, so now I want to do, which part is the next one? The DeMorgan Law, part B, I think. Make sure I do the right one. Yeah, so we're going to now prove this thing about x minus a union of a bunch of stuff is equal actually to the intersection of x minus ai. And DeMorgan, that name came up before when we had logic. We'll see this happening in the proof actually. If you compare this to one of our negation rules, which was something like, if you had some propositional form that's an or statement and you're negating it, you'll remember that the or became an and. When you push the not inside. And you know, union, as I said, is a little bit like or, and intersection analogous to and. That's kind of the idea of why, and subtraction, sets and set difference is like a not. That's kind of why this thing is going to flip. X minus a union, set difference to union is the intersection of the individual set differences. That's what this particular result is saying. And, okay, so it's a set equality. Assume we've already fixed the x and the I and all those things. Those have already been fixed at the beginning of the proof. How do you prove a set equality? And you're all saying to your computers, well, one of two things, either a two-part proof or maybe a chain proof. It's not always clear that the chain proof would work. Let's do two-part proof. Let's do a two-part proof. Or I won't do the whole thing, but I'll do one of the two parts after I set up the two parts. And when I say two part, that means we have to do the subsets in both directions. Prove left set is subset of right set. And part two is prove the right set, in this case I'll actually write it down, is a subset of the left set. And as customary in these two-part proofs, which are the two parts are very similar, I'm not going to take time in the video to do both parts. I think in the book I did the first part. Is that right? So I'll say omitted here, but see book where I think it's done, or you can try it yourself for practice. Of course, in your homework, you never get to do this. You don't get to omit the two parts or one part. But obviously, for time reasons, I get to do that in some situations. But let's do part two on the video together, so whatever that means. Subset proof, right? And so we just launch into the subset proof template. fix arbitrary, let's call it Z, whatever letter. Z seems good. Assume Z is in this left-hand set. Whatever it may be, this whole long thing, I don't care, just write it down. Prove that Z is in this right-hand set. Whatever it may be. Okay. Well, now we've got tons of definitions sitting in front of us. Let's work through them slowly, expanding what we've assumed and what we have, what we must prove. Definition of general intersection, we've assumed for every I in I, Z is in the set X minus AI. So continuing, just to say that even a little bit more, we've assumed, because the set difference is a defined concept as well, for every I in capital I, Z is in X, and Z is not a member of A sub I. Definition of set difference got used right there. Still inside the quantifier, by the way. And, okay, so now what do we have to prove? Prove Z is in X. Now I have to do the set difference definition first. And Z is not a member. Here I'll actually use the word not. Not, Z is a member of the union of the AIs. Okay, and what does that mean? So prove Z is in X and not, we'll do it one step at a time. All right, what is this definition? This is the union definition. Inside the not, I haven't done the denial yet. So this means there exists an I and I. Let's actually change that letter. Let's make it a K just to be safe. Going back to this comment over here. Z in A sub K. All right, if that looks weird, but what I've really done is I've changed this to a K just to avoid any possible conflicts with the I in the assumption, the little I. Okay. Ooh, and so now we get to deny this because it's inside the not. We're denying an existence, and again, this is sort of the crucial why the thing flips over. So what we're really proving is that Z is in X, and for every K in I, for every index in I, Z is not a member of AK. So the not has now been sort of processed. All right, keep going, right? Every time so we've finally expanded enough stuff in the goal. The goal is now an and. So part one. Inside part two, part one of the and statement, maybe call it part 2A or something, we have to prove that Z is in X. Okay. Now this is actually a little bit weird. So look, here's the assumption, by the way. But there's a little something fishy that happens right here, which is that you can say, okay, wait, I have a known statement here. Z is in X. It's just assumed right there. The trouble is, that's only true for things in the index set. Okay. And this is where the assumption, which I said a long time ago, I don't know if it's currently on the board, but throughout the lecture, the index set is assumed to be non-empty. Okay. And that actually gets used right here. Because the index set is not empty, there is some I, call it I naught, maybe, in I, and for that choice of, because you have to choose this thing here, in the known for all statement, you have to choose an index. If this was empty, you wouldn't be able to do that. Call it star. So choose I equals I naught in star, and then you get that z is in x and some other thing is true as well. Some and statement comes out of this. For now, we don't even care about this, but now we got this thing as something we know. So z is in x. That's one of the reasons that you're wondering again, why the index set. Weird stuff happens if the index set is empty. So I won't ever consider that case in what we do. Okay. The union actually can work, but the intersection sort of has problems when you have an empty index set. And here's a case where that actually came in a proof. Anyway, part 2b, so now we've done, remember this is the goal, here's part 2a, now for part 2b, we have to prove this guy for all k and I. Z is not a member of AK. Again, sorry for the clutter and so forth. Anyway, look, so now we have a goal that's a universal statement, as opposed to a known universal statement, which we have right here. Okay. So in this goal, we go on with the proof template. Fix an arbitrary, let's call it k naught in I, to emphasize the variable has been replaced by a particular generic constant in the index set, k naught. We have to prove that z is not a member of a sub k naught. And how are we going to do this? Again, you have to keep track of everything. This assumption is still available. It wasn't from part 2a. It's a global assumption in part 2 of the whole proof. Okay, so it's still true, or assumed. This is known, a known universal statement, about every I. Every single index in I, whatever you choose to call it. Well, here's an index in I, k naught. So by the inference rule for all, by definition of all, if you want, I can replace this little I here by k naught. So by definition, I'll say it like this. By definition of all, we can let I equal k naught in star to conclude, well, actually two things. Z is in X, which in this, we don't actually care about that here, but we also get that Z is not a member of AK naught, a known AND statement. So by definition of AND, the second thing, the second piece of the AND the first piece, but they're both true. The second piece gives us the thing we need to complete part 2b. Okay. And with those two parts, we've now proved this. We've therefore proved everything, works up the stack, and we've basically gotten through this set conclusion. So we're now done with the whole theorem, provided that somebody, you or me, somewhere has done the other part 1 and proved that. All right, so this isn't the end of the lecture, but I'm going to cut the video here and make another one, so we'll have 2 parts just in case anything goes wrong. And we'll have a couple more proofs and like a little set builder thing in part 2 of the lecture. So here we go.